Okay, chapter 18 is your applications of your derivatives. So this is where we get into SVA. Okay, this is the critical language of motion. So if you want to pause the video and get this written down, one thing I'm going to talk about here when we talk about SVA, S is our position function or displacement, and derivative of position is velocity, derivative of velocity is acceleration. This is the derivative side going this way. So going backwards is the antiderivative. So you have to really understand this. The other thing, speed is the absolute value of velocity. So say that we throw a rock up in the air. On the way up, its velocity is positive. At the top, the velocity is 0. And on the way down, the velocity is negative because velocity shows direction. Positive up, negative down. At the top is 0. Now, speed though is always positive. So on the way up, the velocity is going to equal the speed. On the way down, the velocity, I'm going to go that backwards here. Speed is the absolute value of velocity because velocity is negative, but speed is always positive. Okay, so the very first thing we're going to talk about, first of all, a lot of times we'll talk about a particle motion with regard to the origin, and this is the particle movement. This is going to be your position graph. Notice the S of t here. So displacement is its position relative to the origin. Okay, now if position is positive, that means P is to the right of the origin. If position is negative, it is to the left of the origin. So I want you to think about there's a difference between distance and displacement. So say that I have this number line, and here I am at 5. If I go 3, now let's go 1, 2, 3, 4, 5. If I take 5 steps to the right and then 2 steps back, I traveled a distance of 7 steps, but my displacement is 3. I am 3 from where I started from, but I traveled a distance of 7 steps. So we have to be careful when we talk about distance and displacement. All right, so there's just one example. It says a lighthouse is situated on the top of a cliff. Look here. Somebody threw a stone out the window and it comes back down. The stone falls past the base of the lighthouse and lands after 6 seconds in the water below. So they give us, first of all, our displacement formula function, and they give us an interval. Anytime you are given an interval, circle it, write it down inside the box, make sure you're paying attention to it because those are the only values we can look at. Also, if it is time is always positive, so be very careful with that. So let's think about this. Initial displacement, the first value it starts as 0. So I'm just going to find S of 0, plugging 0 in for t. S of 0 is 25. B, use quadratic theory to graph S of t. That sounds kind of confusing, but it's just, this is a quadratic. How do you graph a quadratic? So let's think about, I'm just going to start it over here. First of all, 0 is at 25. So see, this is this first point here. We need to find the vertex. So one of the things I'll draw your attention to is the axis of symmetry in a parabola goes right through the vertex. If you look in your formula booklet, the axis of symmetry says x equals negative b over 2a. A, B, C. So I'm going to find my x value by doing negative b over 2 times a, which is negative 2. Okay, so my x coordinate, oh, this is negative, sorry. So that makes that positive. It's like that doesn't make sense. Okay, so my x coordinate is 2. So then I'm just going to plug 2 back in to my equation, and I get 45. So what that means is 1, 2, 3, 4, 5, 6, because it says it wants us to graph on this interval. So I have 0, 25. This was 25, 30, 35, 40, 45, 2, 45. I'm going to also find my x-intercepts from my equation. I'm going to factor out negative 5, divide everything by negative 5, because then this makes this part easier to factor. This negative 5, remember, that's what makes it go upside down. T minus 5, t plus 1. So t equals 5, t equals negative 1. So remember, time cannot be negative, so we're not going to use this one. This is telling me this is going to cross the x-axis at 5. So my graph's a little bit off here, but we got to start from 0, go up to 6. Here's my vertex. There's my graph. At what time and place does it change direction? So at the top here, at this point, at t equals 2 and 45 meters, the rock changes direction. Then finally, at what time interval is it above the ground? Starts at 0 and it's above the ground until it gets to 5. That's why this was important here. So I'm going to say on the interval from 0 to 5. Don't say 5 seconds. It's asking specifically for an interval. So make sure you answer in an interval. So sometimes what we do is rather than graph it, we write it into a motion diagram. And that was back from here, right here. This is also called the motion diagram with respect to the origin. So here's our origin. We started at 25 because this number line at the bottom is the position function. And then what you do, you put an endpoint where it starts, and note that this is time 0. At time 2, it's at 45 position, and it changes direction and starts going back to the negative side. At time 5, it's at position 0, and at time 6, it's at negative 35. So from time 0 to time 5, it is to the right of the origin, and from 5 to 6, it's to the left of the origin.